In the sturdy framework of materials and structures, there exists a foundational and analytical discipline known as solid mechanics, a branch of mechanics that delves into the behavior of solid materials under various loads and conditions. This narrative, grounded in principles from classical physics, material science, and mathematical modeling, unveils the story of stress, strain, elasticity, and the fundamental principles that govern the deformation and stability of solid bodies. Stress and strain. At the heart of solid mechanics lies the interplay between stress and strain, the fundamental measures of how a material responds to external forces. Stress, the force applied per unit area, induces deformation in the material, leading to strain. Understanding the relationship between stress and strain is pivotal in predicting the mechanical behavior of solids. Mechanical properties. The narrative deepens with an exploration of mechanical properties, including elasticity, plasticity, and ductility. Elastic materials return to their original shape after deformation, while plastic materials undergo permanent deformation. Ductility characterizes the ability of a material to undergo significant deformation before failure. These properties shape the material's response to applied loads. Material models. Solid mechanics unfolds with the use of material models, mathematical representations that capture the behavior of materials under different conditions. Linear elasticity models describe materials that deform elastically under low stresses, while nonlinear models accommodate the plastic deformation of materials under higher stresses. These models guide the analysis of structures and components. Elasticity and Hooke's law. The discipline introduces elasticity, a key concept where materials deform reversibly under applied loads. Hooke's law, a fundamental principle of elasticity, states that the deformation of an elastic material is directly proportional to the applied stress. This linear relationship forms the basis for analyzing the deformation of structures under small loads. Plasticity and yield criteria. Solid mechanics delves into plasticity, a regime where materials undergo irreversible deformation. Yield criteria, such as von Mises criteria or Tresca's criteria, define the conditions under which plastic deformation initiates in a material. Plasticity analysis is crucial in designing structures that experience significant loads. Structural mechanics. The narrative extends to structural mechanics, where solid mechanics plays a central role in analyzing and designing structures. From beams and columns to bridges and buildings, the understanding of stress distribution, deformation, and stability is essential for ensuring the safety and efficiency of structures. Buckling and stability analysis. Solid mechanics explores buckling, a critical phenomenon where slender structures can fail due to instability under compressive loads. Stability analysis involves assessing the equilibrium and deformations of structures to prevent catastrophic failures. Understanding buckling is crucial in designing tall and slender structures. Finite element method, FEM. In the realm of numerical analysis, solid mechanics embraces the finite element method, FEM. FEM involves discretizing complex structures into smaller elements, allowing for the numerical solution of complex stress and deformation problems. FEM has become a powerful tool in simulating and optimizing the behavior of structures. Fatigue and fracture mechanics. The discipline extends its reach to fatigue and fracture mechanics, addressing the response of materials to cyclic loading and the propagation of cracks. Understanding fatigue and fracture behavior is crucial in assessing the durability and integrity of materials in applications ranging from aerospace components to automotive structures. Applications in material science. Solid mechanics finds applications in material science, guiding the development and characterization of new materials. The understanding of stress, strain, and material behavior contributes to the design of advanced materials with tailored properties for specific applications. Biomechanics. In the realm of biology and medicine, solid mechanics plays a role in biomechanics, a field that applies mechanical principles to study the behavior of biological tissues and structures. Biomechanics contributes to the design of prosthetics, understanding bone mechanics, and optimizing medical implants. In essence, solid mechanics is the architectural blueprint of materials, a discipline that, through the lens of stress, strain, and material behavior, ensures the structural integrity and functionality of materials and structures. It is the discipline that, in the vast landscape of engineering and material science, guides the understanding of how solids respond to the forces imposed upon them. In the grand narrative of mechanics, solid mechanics stands as the meticulous architect, shaping the structures and materials that form the foundation of the physical world.